I will begin with a word of prayer. I will attempt to begin with a word of prayer. Dear Father, we thank you for this day, and I just pray that you'd guide our steps, and we just thank you again for all your many blessings to us this semester, Lord. Help us to finish this semester well, Lord, for your glory. In your name I pray, Lord Jesus. Amen. So, I wanted to show you how to solve some things today. So I want to talk about differential equations over an algebra. So the algebra A I have in mind, it's still something like Rn paired with multiplication star, let's say. And so just to summarize, we can talk about a function from A to A is A differentiable if the differential of f at some point P is in the regular representation of A. Now here, if I use x1, x2, xn for coordinates on Rn, then this condition that the differential of f at P be in the regular representation of A is interchangeable with the following partial derivatives. So it's interchangeable with saying that partial f, partial x I times Vj, Ej here, is equal to partial f, partial, get it right eventually here, Ei times partial f, partial xj. So notice that the I and j have switched places. These are the so-called symmetric A Cauchy-Riemann equations. All right. And so basically, if you can find a function and it's continuously differentiable, and it satisfies these symmetric A Cauchy-Riemann equations, that suffices to say that the function is differentiable with respect to the algebra. Furthermore, if E1 is equal to the identity on the algebra, then you can also, then of course E1 times anything is just anything again, right? It's the multiplicative identity. So these Cauchy-Riemann equations simplify considerably if we look at the case partial f, partial xi is equal to partial f, partial x1 times ei. And oftentimes this is kind of the nicest form of the Cauchy-Riemann equations. So for example, if I have, say, the complex numbers, right? So here we have E1 is 1, we have E2 is the number I, right? So then partial f, partial x2 would be equal to partial f, partial x1 times E2. All right. That would be the Cauchy-Riemann equations for the complex numbers written in this notation. Now usually we do what? We put x1 equals to x and x2 equals to y, and we set f equals to u plus iv like that in the complex analysis course. Some of you are taking it with me. Others of you have taken it with Dr. Sprano like last year, right? So this should be familiar, what I'm about to write, so we've got partial f partial y is equal to partial f partial x times I. But, you know, in detail, that's uy plus I vy is equal to ux plus I vx times I. And so what's that give us? That gives us IUX minus Vx. So equating coefficients of imaginary and real components, what do we got here? I see Uy equal to what? Minus Vx, right? And I see Vy equal to Ux. And of course, those are the usual Cauchy-Riemann equations, right? So what I'm showing you is just a way to generalize that idea for an n-dimensional algebra. I don't want to belabor that further, but my point to you is what I'm doing is a straightforward extension of complex analysis, all right? I showed you a paper yesterday, Monday, where all of the usual laws of calculus from calculus 1 to calculus 2 have been developed over an algebra. These things I've worked out. So, you know, product rule, chain rule, also power series work just like you'd expect. So I'm going to jump ahead to that. Definition. E to the z is the sum n equals 0 to infinity of z to the n over n factorial, right? So this is 1 plus z plus 1/2 z squared plus dot 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 dot. So this is the exponential, and this is for any algebra A. Now, I say any algebra A, but what I really mean by that is finite dimensional. It's a finite dimensional associative unital. And possibly commutative. I mean, some of the things I'm going to tell you, let's just, you know what, let's just tack commutative onto it. I don't think I have anything non-commutative to tell you today, so let's just, for the purpose of today, assume commutative as well. All right. But my point to you is this exponential function is defined for any algebra by the power series. This definition works for complex numbers, hyperbolic numbers, 3 hyperbolic numbers. You pick at any of the examples of algebras I've showed you, that's the exponential function, and it satisfies the usual properties. What are the usual properties of the exponential function? How about this? If I have e to the z times e to the w, what do I get? To the what? E to the z plus w, yes, that is true. Now, if the algebra was not commutative, then I'd have things to worry about. But I'm assuming commutative, okay? So e to the z times e to the w, e to the z plus w. What about e to the 0? It's 1 plus 0 plus 1/2 0 squared. I mean, it's 1, right? E to the 0 is 1, where 1 is the multiplicative identity of the algebra. All right? So what can you tell me about the exponential? What can you tell me about e to the z times e to the minus z? What's that give us? E to the what? You got 1? Yeah, e to the z minus z. E to the 0, which is 1. What's that tell me? E to the z is an element of what? The units of the algebra, which in my papers I sometimes write like this. Yeah. So can the exponential be a 0 divisor? No. It's an invertible element. And these properties can be proved at the level of series without regard to the particular choice of algebra. You can similarly define cosine, sine, cosh, sinh, all of your favorite functions you can define over at algebra by their power series. And they will satisfy all the usual identities that they usually do. That's in the paper I wrote with Daniel. Now, so getting to the point here, if we look at e to the, say, lambda times z, right, and we differentiate that with respect to the algebra variable z, there's a chain rule. The chain rule says that, oh, the other bearing the lead here, guys. What's d dz of z? d dz of e to the z is what? E to the z, right, yeah. So the kind of embarrassing thing about calculus over in algebra is people who know nothing could do it. You could find someone completely ignorant of abstract algebra, an engineer, for example, and you could have them do a calculus. It would be fine. They would do it. It wouldn't even be an issue because you just follow the same patterns. I mean, and this is why complex analysis is so beautiful in part, is because people who have very little mathematical sophistication can still do complex analysis correctly because it mirrors real analysis. And as long as you avoid asking the wrong question about a branch cut or something, you're pretty good. But those same questions math majors have trouble with, so we might talk. E to the lambda z, d dz of lambda z, right? That's the chain rule. This we can prove for an arbitrary algebra, composition of functions on an algebra. Here we're looking at the composition of the outside function exponential. The inside function is g of z is equal to lambda z. All right, that's the composition of functions, the exponential, and the multiplication by lambda. Here I'm assuming lambda is constant in some algebra, and I'm assuming that z is an algebra variable. Right? So in complex analysis, we teach you how to deal with complex variables. I'm telling you that you can level it up. You can talk about algebra variables. And, okay, well, what is this? What does this differentiate to? Again, you know the answer even though you haven't proved it. Lambda e to the lambda z. And what happens if we differentiate the exponential function n-fold times? What if I say d dz is equal to big D? Taking a chapter from, a la Math 334. Right? If you've had differential equations, you're familiar with the big D notation for differential, right? Well, let's go down that road. So what would d to the n acting on e to the lambda be? Lambda to the n, e to the lambda z. Very good. So let's look at an example. Let's look at the algebra, which is kind of interesting. Let's look at the reals, direct sum with I times the reals, direct sum with j times the reals, direct sum with ij times the reals, where a is commutative, and I squared equals to j squared equals to minus 1. This notation plus circle means the direct sum decomposition. It says that the things that you're adding together are independent. So all I'm really saying is that I'm thinking of I, j, the number 1, which I just don't write as a matter of convention, right? I mean, you could write 1 here. Un. It's there. So when I write this notation, it's just a shorthand for me saying I'm looking at A equals to R4, where E1 is 1, E2 is I, E3 is J, and E4 is IJ. This notation simply means that. All right? And that's in complete and total agreement with my usage of plus circle for direct sum decompositions in linear algebra. If you had my linear algebra. So, is this an algebra? Does this thing close? Like if I take sums of products of these, is it going to go back to where it started? Like what happens if we multiply? I mean, let's take a breath here and multiply out a couple of these numbers. So when I say number, I mean something rather general, right? Some people, when they talk about a number, they have an insistence that division's defined. I make no such assumption. For me, number, just something that I can multiply in the natural way. Zero divisors don't bother me. So if you insist on no zero divisors, then your possible number sets are much smaller, right? You've got reals, complexes, quaternions. And then finite field stuff, right? There's lots of that. But let's look at, how about A plus BI plus CJ plus DIJ times X plus YI plus ZJ plus WIJ. What happens when we multiply these out? Let me collect everything that's just got the number 1 in it. So we got AX, BI, we got minus BY, minus CZ. Hey, what's IJ times IJ? Can you guys tell me? Ah, so it's minus 1 times minus, yeah, you told me. It's 1, yeah. So we got plus DW. And then what's my I terms? AY plus, we got B, BX, yeah. Can I take C times something and get an I? Oh, C times W, right? Gives me what? These two terms I get IJ squared, which is what? So I get minus CW, right? And then this times, to get an I, dy minus dy, right? That's all times I. And then what's J? What's the coefficients of J? Hey. Thank you. Eventually I'll learn how to multiply. Although in my defense, I think I've only multiplied in this algebra once before in my life. Although I might have done it 5 years ago. I forget what I did 5 years ago. I don't know. AZ. What we got? Shout something out if you see it. BW? Minus BW, okay. And then C what? CX plus CX, yeah? And then minus D what? DY. And then finally, that's times J. And then finally plus, what's my IJ terms? I've got AW. And then plus BY. No, plus BZ, right? And let's see here. C what? Oh, CY, yeah. We were assuming commuting. And then D what? Oh, DX plus DX. Now, if you do multiply this out like this, you can also, from this, read what the regular representation is. See, because the regular representation is the standard matrix of left multiplication, right? So like, if I take some matrix times X, Y, Z, W, whatever matrix there, that is the standard matrix of what? Of left multiplication by, let's say, alpha, where alpha is this thing, right? So this calculation allows us to, among other things, read off the regular representation of the algebra. This is how I used to always do it. So you guys tell me what's the, so what's this give me? That gives me the first row, right? A minus B minus C, D. This actually tells me what the second row is, but I gotta be careful because my X's and Y's and Z's and W's are out of order. So I got a B, I got an A, I got a minus D, and minus C. We're going to get A's down the diagonal. Next up, for the Z, we've got C minus D and minus B over here. And if anything works out, you can complete the last row by just putting the letter you don't already have. D, although I guess I got to think about signs. Oh, they're all plus. Woohoo. So DCBA. And there you go. That's the regular representation of A plus BI plus CJ plus DIJ in this algebra. Man, I had hoped something. In my head, I had convinced myself that IJ times IJ was minus 1. Yeah? But it's not the case, is it? Nah. What do you guys think? Is this the group algebra of something? Sure. It's like 4 blocks of complex numbers.
And then the top right is negative.
Huh. Ooh. That's actually a really nice observation. So you're like, look at this. That's a complex block. That's a complex block. And these are kind of complex blocks, but that's got a minus on it, right? Oh, but it's itself like a, yeah. I'm guessing that A is isomorphic to C cross C. But I don't want to pursue that in class right now. Yeah.
Okay, so is this just the fact that J squared is equal to I squared?
Mm-hmm.
Last class, we talked a lot about algebras where J squared was equal to 1, or J cubed was equal to 1, rather than equal to negative.
Oh, these are still equal to -1. Yeah. I mean,
But last class, we talked about where J squared was equal to 1.
Right.
-1. So.
Well, the algebra, the n Pythagorean theorem actually worked for plus or minus 1,
Okay.
for example.
So, I guess I'm wondering what. So the 3 hyperbolic numbers, for instance, when you were talking
Right.
about 3 hyperbolic numbers.
Right, right.
Is that where J squared is equal to 1?
Three hyperbolic numbers are the group algebra for the cyclic group of order 3. So they're defined by something. They're defined by something that's the third power is the identity,
Okay.
but like 1, J, and J squared are all independent.
Okay, right.
But then J cubed is the identity.
Okay.
The name of, weirdly enough, the name, if you have J cubed, or I usually use I cubed equals to -1, these define the so-called complicated numbers of order 3. I did not make that up. It's in paper. It's in the paper. So there's some connection with complicated numbers and primes of a certain form.
Okay.
There's a paper by,
So then this really was you just picking I, J, and I. Like this
oh, I and J have no like fixed,
This is just you selecting.
yeah,
algebra.
right,
Just have fun.
indeed. And let's have, so now that we have had some fun with this algebra, let's have more. I wanted to get us a little bit accustomed with how this algebra works. and then try to solve a differential equation in it. All right? So same algebra, all right? And I'm not sure I understand your question yet, Liam, but that's okay. And so let's solve, let's see here, how about d minus I times d minus j acting on w equals to 0, where w is equal to d dz. Now, just allow me a moment here to show you what this would have looked like if I hadn't had a conversation with Dr. Scambortis for class and wasted the time that I needed to create this example to make it more interesting for you. What I'm trying to say is I'm showing you the man behind the curtain right now by writing that, but to make this more exciting, I would multiply those out. In other words, this is the differential equation w prime prime minus I plus j w prime plus ij w equals to 0. We're trying to solve this second order differential equation over the algebra. Now, it's actually obvious how to solve it given my initial formulation of it. Now, if you're in differential equations right now, you probably know what would be a solution to this differential equation. Can you tell me, Taylor, what it would be? One of them? While you're thinking, one of the things I shared, or maybe failed to share with you yesterday, is I have proved the existence and uniqueness theorem, so I already know what's going to happen. This is a second order non-degenerate differential equation. There exists a fundamental solution set of two linearly independent functions over this algebra, and that will form the general solution, just like in differential equations. But here linear independence is linear independence in a module, not over a field. Meaning that, well, let me not get into that, but in other words, I'm looking for w is equal to c1 w1 plus c2 w2. I'm just I need to find my fundamental solutions. This is standard differential equation stuff, yeah? So what should we make w1, what should we make w2? What do you think? E to the I, right idea, but our variable here is z. So, but yes, e to the I z, and w2 would be what? E to the jz, right? jz. I just wrote jx. What's wrong with me? There we go. Indeed, that is the solution. Now, on the other hand, we can look at the characteristic equation. So if we plug in e to the z, plug in e to the lambda z, what happens when we plug in e to the lambda z into the differential equation? W prime prime gives me what? Lambda squared e to the lambda z, yeah? And then I get minus minus I plus j lambda e to the lambda z, and then plus ij e to the lambda z. And if e to the lambda z is going to be a solution, it has to make that be 0. That's a necessary consequence of lambda being the appropriate lambda to solve this differential equation. So of course, as we do in differential equations, you can factor out e to the lambda z, and you got yourself lambda squared minus 1 plus I plus j rather, I plus j lambda plus ij equal to 0. Well, excuse me, all of that times all of that times e to the lambda z equal to 0. But the thing about e to the lambda z is, can it be 0? You're like, I don't know. You got all kinds of crazy algebras going on here. I don't know what happens. No, you do. E to the 0, e to the z is a unit, so it can't be 0. So it forces that polynomial to vanish. It has to be that the characteristic polynomial vanishes. This has to be 0. And so, in fact, it's not surprising that I tell you that this factors is lambda minus I times lambda minus j, yeah? Which shows you that lambda equals to I and lambda equals to j solve this differential. They're the characteristic roots here. All right, so I haven't done anything particularly weird here. It's just sort of, this is not, and I think that I could make this example weirder if I had a little bit more time to see. The thing about working with polynomials over an algebra, so polynomials over an algebra, right? So d minus I times d minus j is actually an element of the polynomials with coefficients in the algebra, like in D, thinking of D as an indeterminate for a moment. In contrast, this thing down here, this polynomial is an element of what? Polynomials in lambda, right? The thing is, we have proved that polynomials are a unique factorization domain, right? Right? We have this f of x is what? UFD, right? How do we prove that? We proved it because we showed that polynomials are in fact a Euclidean domain with respect to the norm given by the degree function, and Euclidean domain implies what? PID implies UFD, right? So polynomials over a field are a UFD, but polynomials over an algebra are not a UFD, which means that if you factored the characteristic equation a different way, you could get different roots. That is, to me, that was very bothersome when I first learned this, because I thought, how can I have more than 2 solutions to the characteristic equation of a second order problem and not contradict my theorem that there's only 2 linearly independent solutions? That seems to be contradictory, right? There's only 2 linearly independent solutions, but my characteristic equation can have more than 2 solutions, even though it's second order. It blew my mind. But in fact, they're not at odds. The thing is, you can have different exponentials with different arguments being linearly dependent over an algebra. So it's just illusory. It's illusory that there are really more solutions. There aren't more. One of your homework problems is kind of about that. All right, so what do we do then? Check this out. So if I'm solving y prime prime plus y equals to 0, all right? And we can keep it real here for a minute. Suppose you're solving this in the reals, right? You do what? You go, okay, well that's really lambda squared plus 1 equals to 0. I'm setting y equals to e to the lambda, let's say x, right? So it gives me lambda squared plus 1 equals 0. And then if I want to stick with real numbers, I'm kind of stuck, right? So what do? We go, well, no problem. This means that lambda is equal to plus or minus I. And so y equals e to the ix is the solution, right? And e to the ix, we can work out, it's cosine x plus I sine x, right? And so y1 equals to cosine x and y2 equals to sine x are separately real solutions. This technique is known as complexification. We face the same problem for differential equations over in algebra. Like, what do you do when you can't actually factor? Like, this one was nice. We could actually factor the polynomial over this number system. What do you do when you can't? How do you deal with that? And I'll show you how you do it. So this is the, well, I can't fit it here. I better put it over here. So the technique I'm about to show you, Nathan Bedell came up with this, a lot of it. And he initially called it the stupid solution. But I think that that is incorrect. I think it's one of the most beautiful and wonderful things that a student has ever invented in the context of me working with them. And here it is. Well, it's not an example, it's a technique. To solve d to the n plus, let's say, an minus 1 d to the n minus 1 plus plus a2d squared plus a1d plus a0, all of that acting on w equals to 0 for these coefficients a0, a1, all the way out to n minus 1 in the algebra. And here d equals to d dz for z a variable, yeah. So to solve this, here's what we decided we'd do. We consider a prime, where a prime is the complexification. Well, it's an extension of a. And the extension of a is going to be this. Oh, I need to give this thing a name. Let's call that thing P of D. So here's the a prime is going to be this. It's going to be polynomials over a mod the ideal generated by P of x. Kroneker's theorem works over a ring just as well as it works over a field. And so this looks like things of the form C0 plus C1 alpha, well, let's say C1k, plus plus Cn, and Cn minus 1, k to the n minus 1, such that C0, C1, Cn minus 1 are in the algebra, and here k is the coset x plus the, like that. It's the usual factor ring. But what we do is we form the factor ring quotienting by the characteristic polynomial of the problem. Yeah?
Just a quick question.
Uh-oh.
That's the ideal. It's mod the ideal of px. So should that be wangle wrangle?
Oh, is that our notation? Yes. It's been so long. I had Thanksgiving and such. I've forgotten my langles and my wrangles. Yes, thank you. Langle wrangle. Langle wrangle. There we go. We've been langled and wrangled now. All right, so great. This is a new algebra, which is even bigger than A. It's n times as big as A in terms of dimension, all right? If A is n dimensional and we're looking at let's say A is k dimensional, oh, bad term. A is m as in mommy dimensional, then A prime would be mn as in mommy times nanu dimensional. It's a big algebra, the extension algebra. But it's an algebra, so I can still define the exponential. The exponential still makes sense. I can talk about the exponential function from a prime to a prime. Same old, same old. And then what I can do is I can look at f of z equal to e to the kz. This is going to be, defines f that's mapping from the algebra to a prime. This isn't straight. Actually, this is exactly what we're doing in the complexification technique if you really look back at it. See, because this really, you're looking at f going from the reals to the reals prime, which is equal to the complex, which is, by the way, r of x mod this. It's like Nathan's not working in the dark here. I mean, his thought process is legit. This is exactly what you should do. And the beautiful thing about this is a prime is essentially a cross 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 a. How many times? N-fold. N-fold copies of a. The basis is 1 k squared, da 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 da, k to the n minus 1. So that means you can look at component functions, much like your homework problem where you looked at component functions of a ring homomorphism. We can look at the component functions of the exponential, right? And here's the theorem. The component functions of the exponential, the component functions of f provide general solution set to P of D, W equal to 0. This is how you can solve any constant coefficient non-degenerate nth order differential equation over any finite dimensional associative commutative unitive algebra, period. So here's an example. If I wanted to solve, this is a rather silly example, but it's a good one, y prime prime equal to 0 with this method. And let's just look at real differential equations for the sake of being specific here. So my a is equal to r. My a prime would be equal to r of x mod what? X cubed, right? So that is things of the form a plus, let's say, bk plus ck squared, such that what? K cubed is 0, and a, b, c are real numbers. That's I call this a prime the characteristic algebra of the differential equation. So what's the exponential of xk, e to the xk here look like? It's 1 plus xk plus 1/2 xk squared, 1 over 3 factorial, xk cubed. But I hardly needed to write the last term because it was what? It's 0, right? K cubed is 0, k to the 4th is 0. So the exponential series truncates to just the first 3 terms, 1 plus k times x plus k squared times 1/2 x squared, yeah? And from this you can see that the y1 equals to 1, y2 equals to x, and y3 equals to 1/2 x squared. These are the component functions of f, letting this be f of x, okay? Of course, you already knew that because you can integrate 3 times and derive this, right? But we could do harder stuff, like, I don't know, how about y prime prime plus 4y prime plus 5y equals to 0? We'd need to work on the algebra a prime, which is of the form, what? A plus bk plus c, well, a plus bk such that what? K squared plus 4k plus 5 equals to 0. The way to look at this more better is that k plus 2 squared is equal to minus 1. So when I look at e to the kx, what do I got? I just got to use my imagination. I got e to the k plus 2 minus 2 times x, yeah? And then that gives me e to the minus 2x times e to the k plus 2x. But e to the k plus 2x is just like e to the ix in my original complexification example. And for the same reasons of series analysis, that's going to give me a cosine and a sine. In particular, this works out to e to the minus 2x times the cosine of x plus k plus 2 times the sine of x. And so you can see that the fundamental solutions here, y1 e to the minus 2x cosine x, and y2 e to the minus 2x. Now I'm not using the theorem. I'm being a little bit sneaky here because I'm supposing that the coefficient of 1, I'm claiming that 1 and k plus 2 is basis for the characteristic algebra here. So if I read off the coefficients functions with respect to that basis, they should still be independent. And indeed, if you're having differential equations right now, you should recognize those as the fundamental solution set that we teach you, right? But my point to you is this method works for any algebra. So I think Nathan's solution is not stupid at all. I think it's really, really neat. So anyway, yeah. Any questions? So Friday, we will do the algebras, all right? And I think we'll probably wrap up the Lie algebras Friday. So most likely, we're actually probably not going to meet Monday because I think you guys probably could use a day to study, yeah. And also, so that Emily, because Emily's like, you're never going to like take off a day. So now, also to make Emily a liar. So there's that. But now, I've also heard rumors that Friday something interesting will happen besides Lie algebras. So it would be good to be here. I would remind you also that I think there's like, what does it say about having a page of notes on the final in here? If everyone takes the survey. So it only takes one person not reading the syllabus to read that to make it not happen, right? All right, I will, if I have neglected to give a person who's no longer in the course, but I technically should have given an FN by now, if there's some person like that, I'll let them, I won't count them against you. Like if we haven't seen a person here, if there's still a person enrolled who's not currently here, well, that's too strong. But the people who have been generally attending and have turned in work, if all of those people do surveys, then yes, we're allowed a page of notes for the final. So when are surveys done? Before finals start, right? So I have to, I guess I'll have to check on reading day. At the end of reading day, I'm going to have to check the surveys and see that everyone's done them. Of course, they also have to be positive and good, right? You've all heard my spiel before about how to answer surveys, right? Not everybody?
That's what we talk about on Friday.
Oh, it's still recording. Oh, that's what we'll talk about. Yes, we will talk about. I will talk about that on Friday. It's true. Yes, yes, yes. Anyway, thanks.